Hello and welcome to this chemistry lecture series. In this video we're going to look at chapter 15 section 5, which is going to look at the addition polymerization reaction of alkenes. So we already visited addition reactions in section 15.3. What we're going to look at now is how those addition reactions can happen between alkene molecules to form a polymer. So let's get started. Polymerization is the word that we use for when a large, giant repeating molecule is made from smaller molecules. Under the right conditions, alkenes can react with each other in that addition reaction. So we saw earlier how during addition reactions, the double bond or the pi bond in the double bond is going to break, and we add molecules to the carbons that were on those double bonds. Well, in the right conditions, under the right conditions, the alkene molecules will do this, adding additional alkene molecules to themselves, which can then go on and on and on, happening over and over and over again. The type of reaction that we're looking at here is called a polymerization reaction, and it creates a polymer. Polymers are long chain molecules, so very long, large molecules, that are made up of repeating units derived that we call monomers. Monomers are the small molecules that will react together to make the polymer. In this case, what's happening is that an ethene or an alkene of some kind can react with multiple other versions of itself, multiple other molecules that are identical to itself, in addition reactions, breaking the pi bond in the double bond and connecting themselves to each other. What that's going to create is what we call a polyalkene. Polyalkenes are polymers made out of alkene monomers. So whenever we name a polymer, we name it as, whenever we name a polymer, we're going to name it as poly, and then the name of the monomer in parentheses. So a polyalkene is a general term for a polymer made out of alkene monomers. If we wanted to do a specific one, so for example, if we have ethene here and we make a polymer out of ethene, that will be polyethene, like we have here. Polyethene will be a polymer made out of ethene monomers. We can use brackets to show a repeat unit for a polymer. Now, why do we do this? Like we said, polymers can happen over and over and over again, going on for a really long time. We could have 10,000 ethene molecules react in this way, connecting to each other, breaking the pi bond and connecting to other ethene molecules. That will be a huge molecule to actually write on paper. And the molecule itself is the same thing repeating over and over and over again. A repeat unit for a polymer is the smallest group of atoms that when linked together are going to make up the polymer chain. When we grab ethene and we react it with another ethene, what we get is the two carbons from this original ethene with the hydrogens that they have bonded to them that are then going to connect to other ethene with the carbon double bond broken. So they're going to connect over and over and over again. So essentially, that carbon double bond gets broken and these molecules get tied together over and over and over again. We can go and draw this for millions and millions of times or tens of thousands of times. So how do we write a polymer more easily? We use what is called a repeat unit. The repeat unit is essentially just whatever the monomer was. If the monomer was 2 carbons, our repeat unit will be 2 carbons. And that's what this is. What this is saying is that we can grab those 2 carbons from the ethene with the broken double bond, because that bond is broken during the addition polymerization reaction, and then put the hydrogens on it, with then these bonds right here going through these brackets. Those brackets are essentially the part that we can copy and paste over and over and over again that will form the polymer as long as it is. So this is what we call a repeat unit, and it shows just one portion of the polymer that we can essentially copy and paste over and over and over again to get that polymer. So let's take a look at addition polymerization reactions. Now, during addition polymerization, what happens is the same thing that happens during an addition reaction. We have the pi bond on a alkene in the double bond gonna be broken, and those electrons, those two electrons from the pi bond, are gonna be used to create a bond to an additive. Now, that additive in the addition reactions we saw earlier were things like a halide or hydrogen, but in this case, the additive is another alkene. And because of that, these reactions can happen over and over and over again, forming a chain reaction that creates a massive polymer. So let's look at what this will look like with a specific compound. We're going to use 2-chloropentene as or 2-chloro-2-pentene as an example. So here is the skeletal formula for 2-chloro-2-pentene, and here is a displayed formula that we have centered around the double bond to make it easier to see. So we can see that these are the exact same molecule because we have that double bond there on both the molecules. We have a chlorine coming out of the left carbon. We have a methyl group, CH3, on that same left carbon. And then on the right side of that carbon, we have two carbon chain here, that ethyl carbon chain that we see here. And then a hydrogen that obviously we don't see on the skeletal formula because we don't show hydrogens, but will be right here on that same carbon as the two carbon chain. So these two are the exact same molecule. One's a skeletal structure, whereas the other one is just a displayed formula centered around the double bond. So now that we've established that these are the same structure, we are going to see how the addition reaction happens. Like I said, with addition polymerization, it's like an addition reaction. So the first step is the exact same thing that happens with addition. That pi bond here on the double bond gets broken, and the electrons from that bond get used to connect to the carbon in the next alkene. The thing is that when this double bond gets broken and connects to this carbon, that forces this double bond to be broken because that carbon cannot have 5 electrons or 5 bonds, and then that gets used to create a bond to the next alkene, and then the next alkene, and the next alkene, so on and so forth. It just keeps happening over and over and over again, thousands of times, creating these giant polymer reactions. We can see here too with the displayed formula, same thing. Pi bond breaks, connects to the next carbon. The pi bond on that alkene breaks, connects to the next carbon, so on and so forth. It's good to center your molecules around the double bond whenever you have addition polymerization. It makes it easier to visualize. Notice how I've set up both of the skeletal and the display structure to have kind of that double bond front and center and everything else around it. So once this happens, what ends up happening is that the pi bond breaks, so this double bond becomes a single bond, and then we end up with single bonds between the carbons. Same thing with skeletal. Double bond breaks, becomes a single bond. This carbon right here is going to bond to this carbon right here. So this carbon and this carbon are going to end up bonded together. And then this carbon is going to end up bonded to this carbon. Same here, this one with this one, and let me get my orange here, this one with this one. So keep an eye on these red arrows, because as we draw our final molecules of our polymers, what we end up with is this red bonds are the new bonds created by the pi bonds breaking, and these black bonds here are the double bonds that are now single bonds. So this is the original orange carbon. It's now bonded to this carbon right here. And then the carbon that was next to that one, the other carbon double bond, is bonded to the next carbon over. And that keeps going. We put brackets to show that this is going to keep going over and over and over again. And then the same thing here. Those double bonds are now single bonds. And we have our connections between what used to be separate molecules that are now the same polymer. So this showing 3 monomers becoming a polymer. Obviously, it's going to be it's going to keep going, but we're just showing 3. So we're also showing what we call 3 repeat units. This is what used to be the 1 monomer, the double bonded alkene. It is now our repeat unit that's connected to other repeat units. So if we were asked to draw a repeat unit, we will draw this right here. If we were asked to draw 2 repeat units, will you do 2 of these? If we were asked to draw 3 repeat units, we will draw 3 of these, so on and so forth. Now, this is the skeletal formula. Skeletal formula can actually clean up a little because this is showing a very, we're just basing it off the drawing, the skeletal formula we had earlier for the monomer. And we're just getting rid of the one, connecting these two. So this does not look very clean. We can clean that up a little, and this is what the molecule would actually look like. We have our polymer chain, the main body of that chain going through the center, with then every 2 carbons having the methyl and the chlorine group, with the 2 carbon ethyl group, and then connected to the next repeat unit. But this is what the addition polymerization reaction is. It creates these large polymers that we can't show the whole polymer because it will be thousands upon thousands of repeat units. We just show 1 or 2, maybe 3 repeat units based on what the questions ask us, and then we just show that they keep going by drawing those brackets. Now, again, be careful with whether the questions ask you for a displayed formula down here or a skeletal formula like the one on the top. Now, let's talk a little bit about polyalkenes and their environmental impact. Polyalkenes are very common, and they're used for plastics and things like bottles, containers, black bags, things that we consider to be non-recyclables, things that we cannot biodegrade, things that are going to essentially create trash. Because polyalkenes are essentially giant alkanes, because if we look back on that molecule we just saw, this is now all single bonded, right? Might have a chlorine here and there with halogens, but they're essentially just giant alkanes. The molecules are extremely unreactive. They don't break down very easily, they don't react very easily, and so when we create trash out of polyalkenes, polyalkenes end up being these forever plastics. These plastics that don't biodegrade. They create a huge environmental problem. They exist for hundreds and hundreds of years, thousands of years even, and they don't break down. The only viable way that we have of getting rid of polyalkenes is to burn them, because as we saw, alkanes only undergo 2 reactions: free radical substitution, which wouldn't help us here, and combustion. So the only way to get rid of these is to burn them, but that creates a ton of carbon dioxide, and that's gonna change climate, undergo enhanced climate change, contribute to atmospheric pollution, and so that's not really a solution. Since a lot of plastics also contain chlorides, like the one we just saw, it's even worse because then they create hydrochloric acid, a hydrogen chloride gas that goes into the atmosphere, and that contributes to acid rain. So burning polyalkenes is not really an option, which is why there's such an issue, and why we have now switched over to trying to create more biodegradable plastics, ones that actually do break down because they're not made with this addition polymerization method. But that's it. That's it for our polymer section. That is what an addition polymer is and how we can tackle that. In the last section of chapter 15, we're going to look at how to tackle questions regarding addition polymers and different types of questions that you might see in the AICE exam. I will see you all in that last video for chapter 15.